Welcome to Ancient Documentaries. Eleanor Margaret Burbage. In 1950s, she was one of the founders of stellar nucleosynthesis and was first author of the influential B2FH paper. During the 1960s and 1970s she worked on galaxy rotation curves and quasars, discovering the most distant astronomical object then known. In the 1980s and 1990s she helped develop and utilize the faint object spectrograph on the Hubble Space Telescope. Eleanor Margaret Burbage (1919–2020) was a pioneering British-American astronomer whose extensive career significantly advanced our understanding of the universe. Beyond her notable scientific contributions, she was a steadfast advocate for gender equality in the sciences. Born on August 12, 1919, in Davenport, England, Burbage developed an early fascination with astronomy. She pursued this passion at University College London, earning her undergraduate degree in 1939 and a PhD in 1943. During World War II, she served as a caretaker at the University of London Observatory, where the wartime blackout provided optimal conditions for stargazing. Despite societal challenges, she persevered in her astronomical pursuits. In the 1950s, Burbage co-authored the groundbreaking B2FH paper, which elucidated the process of stellar nucleosynthesis, the formation of chemical elements within stars. This seminal work remains a cornerstone in astrophysics. During the 1960s and 1970s, she conducted extensive research on galaxy rotation curves and quasars, at one point identifying the most distant known astronomical object. In the 1980s and 1990s, Burbage played a pivotal role in developing the faint object spectrograph for the Hubble Space Telescope, enabling unprecedented observations of the cosmos. Throughout her career, Burbage encountered and challenged gender-based discrimination in astronomy. In 1972, she declined the Annie J. Cannon Award, which was exclusively for women, advocating instead for equal recognition regardless of gender. Her leadership roles, including serving as the first female president of the American Astronomical Society and as director of the Royal Greenwich Observatory, further exemplify her commitment to breaking barriers for women in science. Margaret Burbage's enduring legacy is marked by her profound scientific achievements and her unwavering dedication to promoting inclusivity in the scientific community. Her life's work continues to inspire and pave the way for future generations of astronomers. Stellar nucleosynthesis is the process by which elements are formed within stars through nuclear fusion and other nuclear reactions. It explains where heavy elements come from and how the universe became enriched with the elements necessary for planets and life. Formation of elements in stars. Big Bang nucleosynthesis. First elements. Right after the Big Bang 13.8 billion years ago, the universe was mostly hydrogen H and helium heat with trace amounts of lithium Li and beryllium B. Heavier elements were not formed in significant amounts during this early period. Hydrogen fusion. Main sequence stars. Stars begin by fusing hydrogen into helium in their cores through the proton-proton chain, in smaller stars like the Sun, or the CNO cycle, in larger stars. This process releases energy, powering the star and balancing gravitational collapse. Helium and carbon fusion. Red giants and supergiants. When hydrogen is depleted, the core contracts, heating up to allow helium fusion into carbon C, oxygen O, and neon Na. This occurs in red giant and supergiant stars. Advanced fusion. Massive stars. In high-mass stars, fusion continues, creating heavier elements like neon, magnesium, and silicon via carbon and oxygen fusion, sulfur, phosphorus, and iron via silicon fusion. The fusion process stops at iron Fe, atomic number 26 because iron fusion does not release energy, it absorbs it, leading to core collapse. Supernovae and heavy elements beyond iron. When a massive star exhausts its fuel, it undergoes a supernova explosion. This extreme environment enables the rapid neutron capture process (R) process, forming elements heavier than iron, including gold O, uranium U, and platinum Pt. Neutron-star collisions also contribute to heavy element production through the R process, as observed in events like GW 170817. Cosmic recycling. The birth of new stars and planets. The elements from exploding stars mix into space, becoming part of new star systems, planets, and even life. Our Sun, Earth, and all living things contain atoms forged in ancient stars. Thank for watching and please don't forget to subscribe.